todos. Voy a presentar a nuestro invitado profesor, Dr. Jindong Tan. Tan es el apellido, Jindong es el nombre. Y el Dr. Jindong Tan obtuvo su doctorado en el área de electrical en Michigan State University en 2002 y había sido assistant associate professor en el departamento de Electrical and Digital Engineering en Michigan Technological University desde el año 2002 a 2012 y actualmente es un associate professor y associate department head del departamento de Mechanical, Aerospace and Biomedical Engineering en la Universidad de Tennessee en Knoxville, los Estados Unidos. Su área de interés incluye Body Sensor Networks, Biomedical Signal Processing, Mobile Robotics, Mobile Sensing. Él ha publicado más de 34 artículos en revistas civilizadas y más de 80 artículos en congresos en esas áreas y sus proyectos han sido apoyados por NSF, el Departamento de Defensa de los Estados Unidos y otros como soportes locales del Estado. Y su plática mañana va a tener otra sesión. Hoy su plática es sobre wearable sensors. Pues espero que es interés de nosotros. También descubrimos las áreas o los intereses intersecciones, tal como, por ejemplo, interfaz, desarrollo de interfaz, esos sí son muy relacionados con el área de computación de nosotros. Pues, sí, al doctor le damos un aplauso.
Thank you. Thank you, Professor Lee. And thank you for coming. I'm really glad to be here to give this talk. This is one of my research area on wearable sensors or body sensor networks. We started working on body area sensor networks in 2005. This work has been supported over the years by initially by a small NSF grant, about 100K. Then we get a NASA support for the use of wearable sensors to instrument the astronauts. Then we get some like Air Force support. Hopefully we can help Air Force personnel with wearable sensors too. Recently we are looking into using wearable sensors for blind navigation. The basic idea is to instrument a blind person so that a blind person or visually impaired can use wearable sound moving in either class environment or on a street. So that's a little. We have graded about 5 PhDs in this area. The first PhD worked on signal processing on heart signal. He's now with Epic Medical System, developing software for medical use. Another one who developed the hardware system for this project went to Apple to help debug the Apple hardware. And a recent one on blind navigation went to commercial spacecraft company, and the 2 others are in academia. So this is where I was when I was in Michigan Technological University. It's not a river; they call it a Portage Canal. This connects 2 sides of the Lake Superior. So Office was there. I was in the electrical and computer engineering department. We started working there. This is something we do not see too much here. You know, this is a trio. Actually, this was a trio, a track that trains take from this area to all the way to Chicago. But now we do not use trains anymore. We converted that to a bike and a walking trail. And in the winter, the snowmobile people would, ride a snowmobile on it. It's a pretty nice place in the winter, but it's very, very cold. Because of that, I moved to Tennessee. I'll show you where Tennessee is shortly. But this is where the campus is. This river is called Tennessee River, and we have a stadium could hold people about 100,000 people. This is for the American football. Tennessee is located around here. This is the East Tennessee area. Knoxville is about here, and Nashville, Professor Lee already mentioned, is about 1 hour drive, 1 or 2 hour drive from Knoxville. So that's where we are located. A little bit about the University of Tennessee. It's established in 1794. We have about 28,000 students, much smaller than IPN. We have students from all 50 states of the United States and about 100 foreign countries. This is about the ranking of the university. Knoxville area has about 180K residents, a small population if you compare to Mexico City. But in the statistical metropolitan area, basically include a few villages and small cities around, we get about 500,000 people. This is about the research activities we are doing. I started my work on mobile manipulation or mobile manipulators. If you heard, like recently, Google acquired 7 companies, and several of those companies try to make a robot with 2 arms and a mobile base can move around. I studied the control and motion planning for mobile manipulators. Then after I moved to Michigan Tech as a faculty, I worked on compressive sensing, basically then I also worked on wireless sensor networks. This is what I'm going to talk about today: body sense networks and biomedical signal processing. I talk about another recent project on insertable surgical camera tomorrow. I also have a student working on augmented reality and visualization for surgery in the operating theater. So that's about my research activities. Body sensor network. So what is the body sensor network? This is a graph when we try to apply for the ISF grant. We thought about, what can we wear on a daily basis for a person that we can help a patient, especially chronically ill patient and seniors. The baby boom and aging population is a big problem in developed countries like Japan and the US. We do not have enough nurses and people to care for them. So motivated by that, we want to develop some sensors that we can wear every day so that we can get all the critical parameters of that person instead of sending that person to a local hospital, which takes pretty much a day for that person to move around and get a medical checkup. Once you have the data, hopefully, this data can go to the cell phone. If you look at this cell phone, it's a very old smartphone, actually, the first generation of smartphone. So hopefully through this smartphone, you can send the data to the hospital. So everybody, relatives, and physicians can get the data. those are pretty much the work or the wearable sensors we have been working on and developed in the lab. I show you a figure of some of those shortly. We developed 3 categories of wireless sensors. The first category is to take vital signs. This is almost the same as when you go to a doctor's office. The nurse take all your temperature like that. Special for this, we developed a sensor that can take ECG, basically the cardiogram, EEG, the brain activities, and the EMG, the muscle activities. Of course, we can do the respiration and the skin, all those stuff. So application for those, we can apply. We can have, the chronically ill people and elderly people or people with sleep apnea to wear that to do a study. Another category of sensor is the human motion capture. Human motion capture is a technique to try to capture how human walks or how human move around. That's a very that's not a recent technique. From at least 100 years ago, people started working on how to actually capture human motion. Now it's quite sophisticated. So our approach is try to develop a wearable sensor approach so that we can capture human motion. I'll talk a little bit more on the potential applications, including clinical gait analysis. If person after stroke has walking problem, how does the doctor help those patients? So that's in that area. Environmental sensors. We were thinking now you can get the vitals, you can get the human motion. What you need is the surrounding or ambient information to help the doctor to diagnose the problem a patient has been through. So we developed like sensor that you can put on the wall to get the room temperature, room moisture, light intensity. We can also localize a person in a room so that if a person falls in the room or somewhere, it can set alarm to call a doctor or relatives. I will mostly talk about human motion capture sensor today, but I show you a little bit about the other sensors we developed. The first one I want to show you is a cardiovascular monitoring sensor. Basically, this is the prototype. This has several layers of board. Each layer does one layer does the ECG, the other layer does the EEG. But if you only need to do ECG, you can only use this. So you can put 2 electrodes here, so this board on the body, then you can get the reading heartbeat. And show it on a smartphone. So this is a video one of my students showed. This is his ECG readings. You can see, a little bit baseline winder everything. You need a lot of processing to make it look good. If you go to a hospital, the ECG looks much better than this. There are 2 reasons. One reason is they are pre-processing. They take the raw signal, they process and make it flat. The other one is you are actually stay still. They ask you to lay on a surgical bed and you cannot move. But this student actually is jumping around. So we want to try and see if this sensor can be worn in daily uses. ECG sensor, that's ECG sensor. For EEG, there are 2 kinds of EEG sensors. One is called the invasive EEG. The other is called the surface EEG. And we did a little bit of invasive EEG, but we cannot do humans or at least without FDA. I mean, not IRB approval. But there's a professor I work with who is in poultry science. So he studied the welfare of chicken. It sounds a little bit weird, but chicken is a big industry. So poultry is a big industry basically. So they process chicken just like, like any other industrial line. So they want to make sure when the chicken is being processed, being killed for meat, they want to study, what the reaction of the chicken. So we hook up a EEG, a surgeon, planted open up the skull of the chicken and put an electrode in the skull of the chicken. Then let it heal for 4 or 5 days. Then after that, I can plug in this device. This is the device we developed that you can put under the vein. This is the prototype. The smaller one we can put under the vein, the veins of the chicken, so the chicken can walk around for a few days. Then the poultry scientists can study the data. So we do get a kind of pretty good signal. This is the normal living chicken. And I think they try to calm the chicken down. And this happens, this brain activity happens when my student use a pencil to poke the chicken, so the chicken get excited. And this is the chicken being put into the gas chamber. So basically the chicken will die in a few minutes. And you can see the brain activity. This is purely noise from this point. So the chicken passed out. So, okay. So that's a little bit about the vital parameters. I want to focus on motion capture with wearable sensors today. So you may wonder, why do we do motion capture? Actually, almost in all the major hospitals, there's a lab called the motion analysis lab. What they do in this lab is they do this. They put up an optical tracking system. I'm not sure if we have more like the typical Wacom motion capture system or not. The basic idea, in order to do clinical gait study, they instrument a person with those kind of small beads, and this is photosensitive. And in the motion lab, they have this camera. This is the high-speed camera. So patient wear them, and they ask this patient to walk around stairs, maybe to jump off. In this situation, during the rehabilitation, they also instrument this person to see how the people get recovered from the loss of function, motor functions, also in this situation. But this can only happen in the lab. They cannot happen outside because the tracking volume is quite small, and to set up a pretty good tracking lab, the equipment is kind of very expensive. It's costing me about 100K to buy a set of 6 or 7 cameras to instrument a small tracking room, which is about 1/8 of this room. It's a very small tracking volume. So the idea is, can we actually use wearable sensors to do similar motion capture? Basically, you can replay that person's motion after they move around. Traditionally, we have different technologies that can do motion capture. So for the wearables, you can see those are the wearable ones. This is the optical tracking, and this is the recent commercial inertia base. Inertia means accelerometer, gyro, and magnetometer. People have developed also sound base. Basically use sound to do localization, and you put the sensor on body and in the environment. So hopefully by the time of flight to infer the motion of our rigid body, or electromagnetic wave-based like infrared or laser. This is pretty common. Now people can use the Microsoft game controller that what they call the Kinect to do something similar. So this is optical base. What we wanted to do is we first want to do inertial motion tracking, and inertial motion tracking has some problem which I'm going to address a little bit. So we are looking into integrated vision and inertial sensing So hopefully we can do more than motion capture. I'll get on to a more on that. So if you look at the motion capture, basically it's orientation tracking. So that's an inertial sensor or inertial device tell you the orientation. So if this is the inertial sensor, when I rotate it around, I get the orientation of it. If I put those inertial sensors on human's body, because the orientation change of each limb or each bone, so you can infer the human joint angles. The problem is accumulated drift. For orientation tracking, if for commercial gyro, those used in airplanes, that's super expensive, very big, but you cannot put on human. For those very small sensors, you almost have one in every smartphone nowadays. It's very cheap. It costs only a few dollars, if not less. But it's not very accurate. After a few seconds, the readings will not be very accurate anymore. So the question is, how do you use a very cheap MEMS sensor to develop a device and the associated algorithm to track a human in a long period of time? The second one is for indoor navigation. This is a little bit related to human tracking, but we are more looking into if when a person walking around, can we always track the trajectory? You may ask, why don't we use GPS to do it? First of all, GPS is not very accurate to track human motion. If you do like a car navigation, that's fine. You map the car or car position with a map, so you pretty much get a rough location. But a human motion tracking, if you want to develop a sensor that allow a person to move around in this room, you only have, a few, centimeters. Half a meter, around half a meter to move around. So you need a high accuracy, and GPS does not work in indoor environment. Again, the problem for indoor navigation is that you have accumulated drift. The sensor is very accurate in a few seconds, but after that you cannot use it anymore. So I want to talk a little bit how we use vision and accelerometer together to do accurate human tracking. The third one is this. See, if you see a video, see like how human is tracked with wearable sensors, or how you navigate a robot in an environment, mostly you are facing an empty hall, no dynamic environment. So there's no other people or cars moving around. But in order to make this device is really useful, hopefully it can work in this kind of environment. And additionally, it could work when both the wearer and the dynamic are dynamic. Basically, if a blind person is wearing while she or he is walking, hopefully he can avoid or she can avoid a coming person or a coming car, just like for those people we can see. So that is the last topic I talk a little bit. This is the sensor we developed. This is still on the board, so my student put on a ruler to move it around to see if you can track the orientation. It seems to be a tracking. I'll show you the performance of these tracking devices. On this device, there are a few sensors, but the key here is how to develop an algorithm so that it does not drift. It always follow your estimation always follow the motion of the sensor itself. This is the too much. The 5 small topics I'm going to quickly go over. The first one is hardware design. So what the hardware look like? Actually, we have been through several stages of this hardware design. This is actually our first stage. It's still a quarter size, pretty big. You get a microcontroller here. You get 3 sensors. One is the accelerometer, the other one is magnetometer, the other one is the gyro. We know the accelerometer measures acceleration, gyro measures rotation rate, and magnetometer basically measures direction in absolute version, in absolute fashion. So this is the architecture for the hardware, but we later find that this cannot do human tracking. Basically, it can track orientation pretty well. It cannot track distance. So how do we track distance together? We put a camera on. This is still a very early version, but most of the result was acquired from this device. This is the board we developed. We bought this camera, so we use a double-sided tape to put them together. We get a vision and MU together. So this is integral MU. But more obviously, this is really bulky. So we look at the commercial wearable cameras. Now you can buy a camera like this for about $10 or $20. So I bought a glass. At that time, we do not have the Google Glass yet, which has everything we need now. But I put on the sensor we have there, and I use this camera to do the tracking. So this is about 2-3 years ago. But now, Google Glass integrated a microprocessor, actually pretty high performance microprocessor on it. Has all the 3 sensors we have here, a battery, and a camera, of course. So it has all the sensors there. So I'm going to show you a video. One of my students used this glass to navigate a hard, blind person. We haven't used human cybernetic study yet, but that's what we have been looking for to get further federal funding. Well, I'm going to cover this part very quick. Now we get the device. The second part is how do you do the orientation estimation? Let's talk about the orientation, distance, and the dynamic environment one by one. So the first one is how do I get out an orientation from here? Did I skip one? Well, the basic idea is I group two sets of sensors into, I group them. The first one is the gyro. Gyro can measure orientation directly. So what's, gyro is, you see a gyro before. I probably, everybody see a gyro before. When you use a gyro, when you rotate it, you measure the angular velocity of 3 axes at the same time, and by integration by integrate that gyro rate, you get an angle, and if you get an angle, then you get orientation. That's pretty simple to understand. So that's what we do. This is what you measure, and when it rotates, you do the integration. This integration is a little bit more complicated than direct integration, but anyway, it's integration. After one step in integration, you're going to get a orientation. But we know when we do integration, what is the problem with integration? You have a variable and you integrate. So the problem is this: if that sensor is perfect, has absolutely no problem, that's okay. We do not need any other stuff. And the algorithm is very easy, just do integration. But all sensors have noise. So when you integrate that noise, you keep adding the noise to the true value. So it only needs 2 seconds actually to drift away from the true value of the exact reading of that orientation. So we cannot use that sensor alone to get the orientation. But that's good. This is very accurate. See, if you keep calibrate that sensor, then we can make it very accurate. But we cannot keep calibrating it. So how do we do? We use the other sensor. One of these sensors is called accelerometer. So what can an accelerometer do? Basically, it measures the acceleration. See, if I have acceleration along this distance, single integration of acceleration is velocity, and double integration of acceleration is distance. But also accelerometers also measures gravity. Even if the accelerometer is not a movement, you always have a reading. That reading is actually the direction pointing to the center of the Earth. That's G. Okay, so that is my gold standard. The gold standard is, I actually know one absolute direction pointing down all the time from this guy. If the accelerometer is not moving, if it's moving, we are going to get a little bit confused. Is that reading caused by G or caused by actually moving? But there's a third sensor called magnetometer. This measures the Earth's direction, the north of the magnetic Earth. Okay, so that is a absolute value, and this one is relative. So if this is the gyro direction, you rotate this way, or this is the gyro direction, you rotate this way, you probably get the same reading but a different direction. But this guy give you an absolute value but not very accurate. When you read the Earth's magnetic field, not very accurate. Also, there's a big problem for the Earth's magnetic field. It's sensitive to metal. If I put a big magnet next to the sensor, can you still get a reading? No. Then your reading will get drifted away. So the algorithm here we have here is to do this. So we use this pretty accurate gyro readings, which is relative for integration, to get the one orientation reading. And we use those two sensors to get some kind of absolute reading. Okay. Then we fuse those two together, use a filter, then somehow, hopefully, I can get, very accurate orientation estimation. So basically, this is the story here. I'm not going to show you all the equations, but they're deterministic based method and the frequency based method people have been trying to use. We have developed one of our own algorithm. I'll compare ours with others. With that, I only talk a little bit of equation. That equation is this. So we know orientation. How do you represent orientation? If you represent the coordinate of a point, you use x, y, z. But for orientation, how do you represent orientation? So you do it this way. One way to do it, see, if this is a vector, and this vector v, the orientation of this vector, you could do this. Okay, I do a projection of this vector to this plane, to xy plane, and do a projection to the z plane, yz plane, and do a projection to the xz plane. I can get one kind of orientation, right? So we get three angles. Actually, there are many ways to represent orientation. One particular way is called quaternion-based rotation. I'm not going to go too much of detail, but this is one representation. They use 4 parameters to represent the orientation of that. So the whole algorithm is based on that. Back to the sensor, this is the reading from the sensor. For the gyro, you read 3 numbers out. Angular read around 3 axes. Accelerometer, 3 readings. Acceleration along 3 axes. And the magnetometer get you 3 readings. The direction. Somehow from those 3, we get this orientation representation. That's what we do in the algorithm. I'll skip the, how did we do the integration and the fusion, and talk about the, show you a little bit of video. This is the experimental platform for the orientation, and this is the benchmark tracking. So we use this to track the orientation of this device, so that we know, our algorithm is good or not. And this is the big, strong magnets. So we try to see if we put a strong magnet to our sensor, if our algorithm can handle it or not. We did several kind of experiments. First, we put the sensor stand still to see if there are any drift, there any orientation change. Then we slowly move the sensor. Then we suddenly move the sensor. Why do we do this? One? Because we said at the beginning we use accelerometer to get the direction to the center of the Earth. But if you suddenly change it, you get a big acceleration. That might mess up the orientation estimation. So when you see if it works when you suddenly change, you have a big acceleration. I compared with a few algorithms, and this is the one, AGOF is the one we developed. You can see instead, if there's no movement, a lot of the estimation has drift or noise, but the one we have actually did a pretty good job. This is the place, when we put the big magnets to the sensor. Okay, so you put a big magnet, it's supposed to drift away, but the algorithm actually can handle it. And this shows when you actually move it, it tracks the true location and true orientation pretty well. This way you move it and put a magnets in it, and also have a sudden fast movement to see if it drifts away. Some of the algorithms like this one drift away, but this one is what we have, did not drift. This is the gyro drift compensation with the magnetic disturbance. We actually can estimate the disturbance from the magnetic field and try to estimate. So you can see we can track it pretty well. Then we look at the accuracy, everything. I'll skip those pretty quick and show you some of the experiment. This is the student, this is the material, and this is the campus. You can see if you put this magnet next to a campus, it's drift pretty big, but this is so the no movement. Her camera is moving, so that's why the video is a little bit shaking. And you can see she put like magnets to it. It's pretty robust, even. But if you put the magnets on the sensor, that's a different story. So there's a little bit of change, but no significant rotation for all 3 axes. Then she'll show this. this is the real, this is the virtual. This is what we estimate. See if it, this video inspection, we have data to compare the root mean square error, everything. It is a fast movement. Okay. So now we know we can use this small sensor to track human motion to do motion capture. But we do not know if we put those sensors on human body, can we get the human motion? Because if you put your sensor here or at a different place every time, you really have to solve the problem of infer the joint motion of each joint of human of the human arm or legs. So we did a little bit of study here. The question is, given still those sensors, but now we might have more than one sensor. Like I put one sensor here, one sensor on the hand, and my sensor here, and my sensor here at the base. So can you actually infer the human motion? See, then that is related to the degree of freedom of a human arm. We actually have quite our arms are very well flexible. We have two degree freedom here, 3 degree of freedom here, and 2 more degree of freedom here. So we have 7 degree of freedom. And for each degree of freedom, you get a variable. That's a theta angle. For each degree of freedom, for example, for this one, how do you measure it? You measure with the angle, let's call it C. And then you can do this rotation, another C. For here, we have 3 C's to describe the motion of the shoulder joint. For here, we have 2, so we have 7 joints together. If we have 2 arms, we consider the waist, we consider the leg, we consider the neck. Suddenly, it's here. So how do we use those sensors to measure that? So another student did a little bit of research here, and the technique we call it twist-based transformation. This is borrowed from robotics. In robotics, basically we develop machines that look like humans so that you can rotate everything, and they develop mathematical models. They call it homogeneous transformation. This is used a lot in computer graphics also. So basically, the rotation of really the body. Then what we did is we modeled the human as a kinematic chain and modeled each parameter in this chain and put it in exponentially rather than the production of 7 metrics. So we do an optimization problem here, try to use the measurement from 3 sensors to infer the theta angles here. So this is basically an optimization problem from this point on, and this is basically the modeling of human motion. We did a little bit experiment also. We tracked the human motion with a motion capture system, which is the red line here. And you can see this part tracks pretty well, but here, it does not track pretty well. So we analyze the reason is that actually when you put the sensors on muscles, it has artifact, and so does the motion tracking system. But you cannot put the sensor directly on the bones, which will be accurate, but you cannot do that. So this is caused by artifact. And our tracking method actually tracks better because you can actually estimate that artifact. So my student did this, and I showed a little bit. This what he did with 3 actions, like arm lift up and fall back, swing left and right, and those markers are, for those this tracking system. So if you look at those 2, they actually respond to each other pretty well for both tracking systems. It's the upper limb tracking. The other one is a full body tracking. He did a range of motions like jumping around. For the sensors here, you can see this is a different student. He put sensors on his body, one here, 3 on the arm. You can pretty much track the human motion. You can see a little bit from this avatar. So this is the MATLAB manipulation of the data. This we map this data to this avatar, and this shows the marker position. So we can use that to do a full body tracking. Okay, now we want to do human tracking, distance tracking. We said, we use these 3 sensors, we can do orientation tracking pretty well now, but how to do distance tracking? Distance tracking relies mostly on this accelerometer. We already said, in order to track a distance, if you can measure the acceleration in 3 directions, tracking is very easy. You do double integration of your acceleration in 3 directions, you pretty much get a distance change in 3 directions, and then you can estimate or you can track the distance traveled of that sensor. But for the same problem, actually, accelerometer drift away even quicker than the gyro. So people have developed a lot of ways to calibrate this accelerometer to make it accurate. One of the typical ways is they put on the shoe. How do they calibrate that sensor when you put on the shoe? Their theory is this: when you put an accelerometer on the shoe, and when you walk, there's always a time instant that the velocity is 0 for that shoe. If the heel actually hit the ground and you place that sensor well. So based on that theory, they actually recalibrate the sensor every step. So for whenever they walk a step, they calibrate the sensor, and they calibrate the distance during one step. But if I keep standing here without walking, then you cannot calibrate anymore. Then the sensor will drift away. Your estimate will not be very accurate. So what we want to do is, we use the operation. See, if I have a camera and have an accelerometer, my accelerometer will drift away, but my camera is still there. I'm still looking at the same thing. So can I use the camera as a reference to calibrate that sensor? Okay. The answer is yes, but the problem is when you are talking about a camera, especially a high resolution camera, there's a problem. See, the camera uses a lot of data, many megapixels, and in order to process that, you need to have a computer, and the computer is not very wearable. So, can we actually develop algorithms that we use the camera, but still can develop a small variable sensor to do it? The answer is yes. The idea is this. We try to do this. We use a single camera, but we do not use that camera very often. Okay. If the accelerometer or gyro detects motion on that person. We start sampling the environment using the camera. Then we look at how the sensor will change and integrate the vision information and the X-ray information together. The basic idea is we reduce the frame rate. Usually, camera sample the environment at a frame rate of 30 or 40 or 50, but we can actually do it in 1 frame per second or even 2 frames per second, and still get a pretty good estimation. Again, this is the sensor we used to do most of the experiment. This is the normal commercial camera, and this is our own device. But now we use this Google Glass to do the experiment. There's another problem I forgot to mention. When you try to use vision to get a distance, there is a problem. In vision, there's no depth. Basic idea in the computer vision community, they actually develop an algorithm to find the orientation of the camera and even track the trajectory of the camera based on the scene. Supposing the scene is not moving. There's a good paper, they call it build Rome in 1 day. What they did is they took a lot of pictures of Rome, and they used a computer to reconstruct the 3D version of Rome. With a few computers, they can do it in 1 day. That means you can actually track the position of the camera and the orientation of the camera, but there's no skill. In other words, the Rome you build is not, they don't know how big Rome is. You cannot measure it. So you need to put the metric information into the pixel. So that is another problem. And when we try to do distance tracking with vision and inertial sensor, we try to infer both information, the depth information. Well, this is a similar diagram I have here. This is still the old orientation estimation diagram, and this is the camera video. This camera video has a capability to do 30, 40, 50 frames per second, but I cannot afford to process them that fast. So what I do is I look at the angular rate, look at the acceleration. You do have an orientation estimation here. So I'm going to use that information to decide how fast I want to sample the environment. I could do 1 second, 1 frame per second, 2 frames per second. Then after that, I look at the features of 2 consecutive frames. Okay, and then compare to decide if this sensor here moved or not, and if yes, how much it moved. And this itself is not accurate, and it does not have a scale. Basically, it gives you a number, but it does not. It's a number, but it's not. You cannot see this 1 meter or 1 centimeter. Then, based on this estimation, I do a baseline recovery, basically trajectory tracking. I compare with this double integration from the accelerometer. I fuse them together, I can do a pretty good tracking. So this is basically the theory, but again, I already highlighted all the equations. So I'm going to skip all the details and talk only a little bit about factor matching. By factor matching, what I mean is, you have a video camera, you do 1 frame, and this is the next frame. By looking at the same features in the 2 pictures, I try to infer how much distance this camera has traveled, and if there's an angle change of this camera. Actually, the small sensor, accelerometer, gyro can do the same thing. So if I fuse those 2 together, I can get a very good estimation of the sensor. We call it a VMU. This is the detail of the equation. So I'm going to skip all the equations, everything, and tell you a little bit the experiment. So we did a little bit of experiment. We put that sensor on the back of the robot, and let robot wander around in the environment. And this robot have a thick laser sensor and its own odometry, so I can know where the robot is. So I compare my estimation with the robot recording. Also, I put it on a small robot arm to move this arm around to see if it reproduces the trajectory of this robot arm. So the first one is a straight line movement. This red is from the robot, and this is the result with we tried two kind of filter. One is called extended camera filter. One is the linear camera filter. It turns out that this linear camera filter works pretty well for this one. For this situation, it works pretty well too. And what I showed here is the scale factor. So basically, you get the depth information. You compare the vision and the MU. You get the you get the ratio, and I can use that ratio to convert the vision distance. This is the trajectory of the robot, and this is the result from the red one is the robot trajectory, and those are the estimations. So this is the scale factor in that particular experiment. If you look at this number, it's different from the previous experiment. It turns out, scale factor is a random number. You only once you start using it, it will be converted from initial number to a constant. It's always a constant for every use. This is the rotation trajectory. This one. The student also did a closed loop system. So basically, you wear this MU, you walk around, make a turn, go upstairs, and then come back. See if the sensor will come back to the same place according to your calculation. It actually did. This is again. Those are the XYZ positions for that closed loop. I want to show you one thing. This is the diagram, the computation time used for computer vision with the increasing number of iteration and factor numbers. And this is what we have. Basically, we developed algorithm that even if we increase complexity of the image, you do not increase the computation time very significantly. And that's how we can make it in real time. And this is the video shows the tracking of the robot. Basically, the dot, the red dot, the red circle are the features used by the computer vision. And the robot is moving in this hallway, and this is the trajectory of the robot. You see, it seems you only see one line, but they overlap to each other. So basically, MU tracks the ground truth very well. That doll used to be my old office, and this is my lab in Michigan. So even in an environment like this, you can track it pretty well. So now I'm ready to talk about the last question. If you look at this tracking environment, you do not see anybody moving around because we did the experiment in midnight. And even if we don't do it and there are people moving around, it's not going to work really well. So we really have to make it work in a real environment. So we don't have to clear up the environment to experiment. And we thought about a good application for this scenario. So we see, if we want to do that because of a good reason, and a blind navigation is a good reason. So suppose you have blind people, and you want to give him a pair or her a pair of glasses, and that glass can do the vision problem. Can do the vision processing of a normal person. What do we need for that pair of glass or for that sensor? I figure out this is pretty much what we need. Basically, you need to know the human motion, human orientation, direction. What direction is she or he facing? Indoor navigation, when I move around, how much distance I move. We need that inference based on our vision. Also, in a static scene, we need to look at this room to see, okay, this is actually the way I can go out, instead of bumping into this chair or use a stick to move around. The last one is when there are people moving around, you can avoid people bumping into people or a car. So we did. This is from the Google Glass, and this is my lab in University of Tennessee. So he wears this glass and move around, and this shows his trajectory. And in this room, we have motion capture sensors, so we compare the estimated distance and the change with the real one. And this shows the readings of accelerometer, gyro, and magnetometer, and this shows the distance we tracked. So how do we do distance estimation in dynamic sense? The basic idea here is you have to segment a scene so that you know which part is moving and which part is not moving. It's not a very difficult problem if we have cameras here, like we have cameras here, and the people move around. We can find what part of the scene is moving. The reason is we always have background. We can extract the background by comparing background and foreground. We know what part is moving. Or in a different scenario, we have a moving camera. See, I have a camera here. I shoot a video. I move it around. I know, which part is moving or not because I'm facing a static scene. But if you have a camera here, the camera is moving around and the scene itself is moving around. How do you separate them? And after you separate them, is it possible or not to estimate the relative velocity? Say you are moving towards me, I'm moving towards you. What is our relative velocity or relative distance? Relative distance is a little bit easier, but relative velocity is a little bit more difficult. After we get that information, I'm able to make a decision if I'm going to bump into you if I continue walking or I need to go. So that's what our current work is. So basically, we model a human motion with something like a Minecraft model, step by step. We also model the same. We didn't use a map, and we try to extract part of the information. So those are the depth map in that Google Glass. We look at this thing, we know which part you can go, which part you cannot. This is the one function. This is a little bit of theory, but basically with those set of equations, I'm able to measure the relative velocity between a moving camera and a moving object. And this shows the result, some of the result. So this is the movement. We did an experiment. This is the marker. We track the marker and track this device, and we move it around. The scene itself is moving. We want to look at the relative velocity. So we can get the camera motion. This is the camera motion, and this is the object motion. And the object motion is tracked also, so we can compare them. My student is developing like a human machine interface with that Google Glass, so you can talk to the glass, see if the scene is clear, if there's somebody is coming Google Glass can talk to you. You can talk to the Google Glass thing. So really, I discussed a little bit about the hardware we developed. How do we do orientation? How do we track distance? And how do we track distance in dynamic sense and the application to blind navigation? If you have any questions.
Muchas gracias.
Thank you.
Interés. Pues la mayoría de nosotros estamos más en la fase de desarrollo de sistemas. Y hablando sobre un tema de Human Interface, nosotros el año pasado tuvimos un profesor, no sé si lo conoce, Carlos Parker, que trabajó en un tesis sobre interfaz, desarrollo de una interfaz entre máquinas. Usamos un smartphone, en este caso de la aplicación de televisión, hay que igual controlar un robot y como una tesis la hemos desarrollado hacia esa dirección. Pues, ¿tienen preguntas o intereses sobre eso?
Yeah, you can use the sensors on smartphone to do the same thing. I don't understand Spanish, but it seems like.
I think it's not on Spanish because it's power.
Yes,
smart power and your computer is faster.
Yes, smartphone is better.
But like not using smartphone, it has a camera, it has initial sensor,
Yeah.
it has wireless communication,
Yes.
everything. Yeah.
Everything you want is on smartphones. It's just when you actually there's a guy did they do blind navigation they didn't do quite what we did, but he wanted to do that, and we wanted to do like a more wearable, like a glass. I showed a picture. We put our sensor to a video glass, but now you have a Google Glass, so we can just use the Google Glass sensors.
Does it need some powerful computer or it has computer?
That's a really good question. Now we reduce the resolution of the image to 480 by 640 by 480. But use the original image. I think it's a few megapixels. We cannot process it. We cannot translate it either.
So how do you evaluate a accelerometer or gyro smartphone? That's the crazy,
No, the sensor we have is much better than the one on the cell phone.
But your computer is nice.
My computer.
It's not on the
Yeah. Even the Google Glass. I think the Google Glass is not as good as the iPhone ones. But you can at least demonstrate. And see the sensor they have, they do not have very good resolution. They only need to know, up and down. It's not we can do way less than a degree over 360 degrees kind of accuracy. But the cell phones cannot. So.
But this is so important because you use, for example, when you use the initial sensor, there's some trick problem. Now you use camera to compensate this problem.
Yeah.
But it's the same if your smartphone is, the initial sensor in your smartphone is not so good, but you have camera. So you can compensate this.
Yeah, that's the camera can do really, really good, but the camera does not have a skill. You move this much, and the camera actually can calculate if you move this much over this much, the ratio of those two movements. They can calculate pretty good with a high resolution camera, but they don't know how much you move. In order to know how much you moved, you really need to know use that accelerometer, which can give you the absolute value, but it's not very accurate. You know, during this motion, it's already drifted a little bit, so you need to overcome back the drift accelerometer to get the absolute value, and you need the absolute value of the camera. I mean the inertial sensor to calculate the distance. So it's kind of it help each other, I guess.
You cannot get all at the same time.
Yeah, you cannot get all from the same. You know, from one sensor you cannot get a box. The video you can see, like with the camera only, you can actually track the position or orientation of that camera really well. But it does not have a CPU. And it's usually when they do, we put a credit card next to it. So we know, okay, this is the size of the credit card. This must be the distance I traveled, or like a quarter in some applications. But with the tool, you do not need that. You only you can actually estimate the true distance.
So I talked to them that we did a thesis work in last year using a smartphone into a smart arm. And as
yeah, I think that's
machine interface.
Okay, you use a smartphone and with a robot. Oh, okay. Control robot. Okay.
Some work and pick up applications and the thing, drop it into the box.
Okay, I see. That's okay.
That's similar to.
Yeah. That's basically you estimate the motion of the human arm based on the smartphone. Then you make the robot to replicate that. Yeah, that's very simple. Yeah.
But the accuracy is not too much, so we tried many times so that the robots can work. Also, the arm is not a very traditional arm. It's very solid instrument.
Yeah, I use a toy arm for this experiment. Now I have a very good arm. I should have fixed it.
Well, in the future we can.
Yeah, we can work together. Yeah, we can work together in that area. Yeah, I think this has a lot of medical applications. I'm working on a professor to do post-stroke estimation. Like you can estimate the human that for the people who suffer the stroke. Sometimes when they walk, that and that's Parkinson's disease. They have a term called the freeze gait. While they are walking, suddenly their brain freeze. So when the brain freeze, they cannot control the muscle. So then they cannot move. Then if they are doing a swing phase during the walking, then they suddenly lose balance and that person is going to fall. So if you put a sensor here on the leg or on the wrist, they might be able to predict if that person is going to fall or not instead of measuring. If it's falling, I can detect that. But before the fall, if I can predict, I can use a device called the Q device that can bring the brain back. If you show like a flashlight or something, actually the brain will come back to normal. But it's not. But we don't know. We cannot constantly do that. If we do it properly, it will help the patient prevent from a fall. And we submitted the proposal to NSF for this. And for stroke, we are doing an experiment with the stroke, post-stroke rehabilitation with this wearable sensor. So when that person is actually doing at home, we can put a accelerometer on their wrist and then to evaluate the improvement of that post-stroke rehabilitation process. So the doctor can see beside the drugs, the physical surgery, that sort of thing.
Actually, we have two small and big between after stroke.
The post-stroke, yeah.
The pueden, por ejemplo, van a poner un poco con esos circuitos que tenemos la rehabilitación. Pero nosotros enfocamos la parte de desarrollo de la interfaz, de cómo entrenar a la gente que controlan más bien entrenar sus neuronas en el cerebro a través de los ejercicios que hacen de meditación. Pues, thank you very much.
Thank you.